this is Ms. Schultz. This is our very first notes in video for pre-calculus. The name of the unit, our very first unit, is Features of Functions. Just so you understand how this works, it's to help you organize yourselves. So this is the unit number. So the pound sign means number, not hashtag. Great. So we're in Unit 1, and this is just the first lesson of Unit 1. That's what that's about. And the first lesson of Unit 1 is about domain and range using NA. What is NA? Ooh, it's the big idea of the whole course. We'll get into it, not yet. So please go ahead and write the date. So since the lesson is on domain and range, let's go ahead and define domain and range. Domain is all of the inputs of a function or relation, aka the x values, and the range is all the outputs, aka the y values. So if you, so domain, you could also say what you substitute in, and then what you get out would be the range, okay? Just a quick reminder, I will not be collecting this. I will be grading you solely on your responses within Play Pause It. So if it helps you to write things down, you should write things down. If it doesn't help you to write things down and you're never gonna reference it again, then honestly don't. You know, you probably know your own learning style best at this point. So just do what works for you. Okay, what is NA? NA is simultaneously number one, it's a strategy for solving problems, okay? Number two, it describes how we're gonna learn things in depth in this class. And it's a thread throughout every unit of how we examine our content. All right, how do we examine our content? So the G stands for graphically. Anything we study, we're gonna look at their graphs. The N stands for numerically. Anything we study, we're gonna substitute numbers into, like numerically, numbers. Numerically, a lot of times people call it tables, okay? So we're gonna make tables of values, okay? So that's the N. A stands for algebraically. Algebraically would be like equations, like, okay? Graphically would be graphs. And then W would be words. Words would be both descriptions of the function, and it would be like word problems. Okay, so for example, I have this poster right here in my classroom. What's up? Okay, so this is an example of the same thing, just represented in 4 different ways. So right up top, you've got a graph, okay? We've got numbers organized in a table. We have the equation of the function written out, square root of x plus 3. And then we have some words describing it. F is a square root function, translated 3 to the left, or you could describe it in words saying F increases at a decreasing rate. That works too, but this is our big idea. So any function that we study, and that's what we're gonna be doing in most units, is studying different functions. You know, like you study lines, then you study quadratics, you know, those are different functions. Everything we do, we're gonna graph it, we're gonna make tables, we're gonna study the equations, and we're gonna describe it and do word problems with it. Okay, so that is our big idea of NA. Let me just re-get this settled here. Awesome. Okay, let's flip. Okay, so we're starting with the G and NA graphically. So we're gonna find domain and range given the graph, okay? Okay, so let's take a look at the first one. So it's a line, great. It goes on and on forever, that's what the arrows mean. You could say a lot of different things about it. So the domain is the x values. It's everywhere that, it's basically where to find the domain, you're answering the question to find the domain, you're answering the question for which x values does the function exist? For which x values does the function exist? So if I look here, let's just take a look. Is the function defined? Exists is like it is defined there. Is it defined? Does the function exist at 2? Yeah, it's -3. What about 4? Yep. Okay, were there any gaps? No, so anywhere this is good. What about 6? The function is defined in 2 places. Actually, it's not a function, this is a relation. Alert! Because it has 2 outputs for 1 input. So this relation, I will not be assessing you on determining whether it's a function. Well, maybe I will. So this is, let's just talk about this. If you have multiple outputs for 1 input, you are not a function. So this is not a function because the justification is important. When I ask you questions like this, like, oh, say whether it's a function or not, I'm gonna also say and why or and justify. Okay, so why is it not a function? Because there are 2 outputs at a certain input. I'm going to be specific here. I'm going to say the input is 6 at 6. Okay? So I'll give you a pause there if you want to write it down. Not a function because there are 2 outputs at 6. Or at, even if I want to be more specific, at x equals 6. Because it's always x values. So the idea is if I give you 6, I want you to tell me where to go. And you can't, do I go to -2 or do I go to -5 or -7? That would be a bad map. Imagine if you entered something in and you're like, okay, I want to know how to get here. And it's like, either turn left or right. You can go to -2 or -7, either one. Like that's what makes it not a function, is that there's 2 different outputs given a single input. Okay, so let's talk about domain and range. The domain is everywhere it exists. So it does exist at 6 though, that's cool. It exists at 2 places, but it exists at 6. What about at 8? Yeah. What about at 10? Yes, even though you can't see it because this line would be extending it, the function does exist at 10. Even at 200, the function would exist, right? Because it's continuing on forever. Over here in the negatives, the function exists in all of the negatives because as this increases, you know, you'll have some value, I don't know what it is, but you'll have some value at like -1,000. It'll be some high value. So the domain is all real numbers. Some people also say all reals. Okay, there's a few different ways to write this. I'm gonna go with, there's 3 other ways to write this, and I do not care which one you use, okay? You could use this symbol for all real numbers. It's an R with like a double spine, okay? You could use the symbol. It just saves you from having to write those 3 words. You could say the graph of the relation goes from -infinity to infinity, and you could write it like that with inequality notation. So -infinity is less than x is less than infinity, okay? So the strictly less than is because you're not equal to infinity, right? So you would never put the or equals to things here when you're using infinity or -infinity. And the 4th way is interval notation. So if you're not equal to an interval notation, you use parentheses. I'll go over this in a minute, more about interval notation. So this basically says you go from -infinity to infinity and all of the values in between. All right, so that's the domain. The range, how far down does this graph go? And how far up? Right, it goes from negative infinity all the way to infinity. So the range on the y's, right? Like all the way down and up. So when you're thinking range, you're thinking down and up. Domain would be left and right. So the range is also all reals. If you're using the inequality notation, it'd be negative infinity is less than y is less than infinity. Okay. If you're using interval notation, negative infinity to infinity. So I don't care which of these notations you use. It's totally your preference. Look, I don't discriminate in here. So if you like the one notation instead of the other, that's great by me, you know? We don't discriminate, so whatever you prefer to use. I will say though, you need to be able to look at any of these notations and understand it, all right? Again, we'll go over this one a little bit more as like throughout this PowerPoint. Okay, let's move on. Let's look at this next graph. What do you notice about it, first of all, that's different? Right, there are no arrows on it, so that means it does not continue on and on forever. It starts at this point, negative 1,7, and ends here at 5,1. So its domain, where does it exist? It exists everywhere in between negative 1 and 5, so domain is x values. And there's no gaps, everywhere in between it exists. Great. It does not go beyond that. So it's not all real numbers because it doesn't exist at say negative 3. Okay, so, and it does exist at negative 1. Okay, so I can say negative 1 is less than or equal to x is less than or equal to 5. Okay, and interval notation, okay, if you have the endpoint being included, okay, you use brackets. I'm going to write that down to summarize for us. So the endpoints are included, then you use brackets. So for interval notation, let me make sure we can see this clearly, interval notation. So parentheses means endpoints not included, and brackets means the endpoints are included. So this is kind of like your less than or greater than, and this is kind of like your less than or equal to or greater than or equal to, okay? And you can do one of each, just like you could do a less than and a less than or equal to both. You can do one of each. We will actually see an example of that throughout this PowerPoint. Okay, what about the range? Why don't you try to think about the range? What's the lowest down on the y's, and what's the highest on the y's? Okay, the lowest y is 1, less than or equal to y, and it does include 1, all the way to 7. Interval notation, 1 to 7. Okay. If you prefer inequality notation, just make sure for domain you write x, and for range you write y. That is quite important. Okay, let's move on. What about this? So I want to show you that these are open circles. Okay, it's hard to tell, it's not a great image, but these are open circles. So that means that the function does not exist at negative 2, at x equals 0, or at x equals 2. They're empty points. All right, so the domain. This function does go infinitely left. It goes super far down, but it does go infinitely left. It also goes infinitely right, super far down. So the domain, but it doesn't go through everything in between. It's just missing 3 points though. So I'm gonna say the domain is all real numbers, except, okay, x cannot equal negative 2, 0, and 2. Okay, make sure you do the x values. It's easy to say that that's like 2 because it's like at 2, but that's y equals 2. Obviously this x is 0, okay? Domain's all about x's, all right? The range, well, how far down does this go? Negative infinity. So I could just start with my inequality notation. I never do or equals to. I always do strictly less than for infinities. And then it goes, what's the highest? Does it go all the way up to infinity? Nope, it goes up to 2. Does it include 2? No. So I'm going to do strictly less than 2. If I did interval notation, it would look like this. All right, let's move on to y equals the absolute value of x. Why don't you try this one on your own? All right, let's group up the domain. It goes all the way to left, all the way to the right. Doesn't miss anything in between, no like open circles. That's what I would be looking for. So the domain is all real numbers. The range, it goes down to 0. 0 is the lowest y value, and I am equal to 0. The endpoint of y equals 0 is included. And I go up towards infinity. Infinity is not included because it's not a real number. So this is an example of where I used a bracket to say that the endpoint was included, like less than or equal to. And then here, parentheses, to be strictly less than infinity. Oops, there we go. If you're not getting these right, that's okay. I get that it's notes. You know, you're learning here. You're experiencing for the very first time this year, so it's okay if you got it wrong. No worries. All right, let's flip. Now, we're gonna do the A and na, so algebraically. Algebraically means we're looking at equations, okay? So my question is so my guiding question for domain is what x values are, I'm just gonna use like allowed. So can I plug in? Let's see. Can I plug in, and by the way, for equations, I'm only gonna ask you domain. I'm never gonna ask you range from equations. I'm just gonna ask you range from graphs and tables. We'll get there. Maybe. Not in this PowerPoint. Okay, so from equations, so what am I allowed, so what x values are allowed here? Can I substitute in 2 and square it? Can I square 2? Yeah. Can I square -2? Can I square -10? Sure. So positives and negatives work. What about fractions? What if I substitute in a third? Can I square a third? Yeah, it's a 9th. Can I square 0? Yeah. So, all reals. All right, that's the domain. You can put in anything. So, what am I allowed to sub in? Okay. If you know what the graph looks like, you could also think of the graph that it goes infinitely left and infinitely right. But yeah, this strategy is going to be the samesies. Okay. What am I allowed to sub in? Can I take any number in the whole wide world and multiply by 2 and then add 4 to it? Yes. So the domain is all real numbers. You might be saying, okay, Ms. Schultz, like I don't get what a situation would be like when you're not allowed to substitute in, right? Aha, we found it. Square roots are one example. You cannot take the square root of a negative number. Let me rephrase that. You can take the square root of a negative number. It's just imaginary, not real. So I'm talking about real outputs here. So I don't want imaginary outputs. I don't want 2i, right? I want only reals. So for the purposes of if I want real outputs, we're gonna say you cannot take the square root of a negative number. So where is this? Okay, let's just try substituting in some stuff. Let's say I sub in 5. Can I do that? Yeah, it's square root of 9, which is 3. Check. 5 is a check. Let's say I substitute in something that doesn't end up being a perfect square, like 1. 1 plus 4 is 5. Square root of 5. Yeah, it's irrational, but that's fine. Again, we don't discriminate. Irrational is fine. Square root of 5, no problem. It's not an even integer. It's not a nice integer like 3, but that's all right. Square root of 5 is just fine. All right, what about negatives? Let's try like -2. If I plug in -2, I get the square root of -2 plus 4, which is the square root of 2. Irrational, but no problem. Yeah, I can do that. What if I plug in -4? The square root of -4 plus 4 is the square root of 0. Can I take the square root of 0? Yes, it is 0, because 0 square root is 0. What about -5? Square root of -5 plus 4. is the square root of -1. That's imaginary. You don't need to know that's I, by the way, if you don't know this. Like, doesn't matter at all. But the point is I can't take the square root of a negative. No square roots of negatives. No square root of a negative. So basically what's in underneath the square root, so what's under the square root has to be greater than, or it can be equal to 0. That's my strategy. That's what I know. I need to say what's underneath the square root has to be greater than or equal to 0. So let's do that. To find the domain, let's do x plus 4 is greater than 0. Subtract 4 from both sides. So I get x is greater than -4. That is my domain. Okay. Let's do this last one. This last one's a little different. It doesn't have a square root, but there are restrictions on the domain. I cannot divide by 0. So you can't divide by 0. Picture something and you're trying to divide it into 0 groups. You can chop it as many times as you want to make it into 0 groups. It'd have to disappear. The matter would have to disappear for you to create 0 groups. That is why I can't divide by 0. All right, so my strategy is what's in the denominator can't be 0. Okay, so I'm gonna take my denominator and wherever it's 0, I mean, this one you can kind of look at and be like, I mean, hopefully you can look at this and say if x is -1, that makes the denominator 0. But in case it's more complex, let's just show out this like method. So you take the denominator and set it not equal to 0. So subtract 1 from both sides. You get x can't be -1. And that's the domain. I like to say that the domain is all the numbers in the whole wide world, all reals, but x can't be -1. Okay? Just to emphasize that this is just one place out of all the infinite amount of real numbers that you can't be. Okay. So, please do some of these on your own, or all of these on your own. So, can you please find the domain of this? All right, the domain is all real numbers, all reals. You can substitute, you can square any number, and you can multiply that by a -1. No problems there, okay? Please do this one. Same deal, I'm gonna explain this in a different way. Well, I'll explain it in 2 ways. You can multiply any number, this is all real numbers, is the answer. Any number you can multiply by -3 and then subtract 4. Another way to think about it is if you think of the graph, well, it'd be steeper than that. It'd be like this. It will take on all the x values, it'll go infinitely left and infinitely right. Okay, so that would be like a graphic approach. All right, please try the next one. Alrighty, on this one, this is all real numbers except x cannot be 3. Because the strategy would be to take the denominator and set it so that it can't equal 0. X can't equal 3. Okay. All right, do this last one, please. All right, the answer is x has to be greater than or equal to 4. So how I get that one is I set the argument, that's a new word, argument, which is aka what's underneath the square root, greater than or equal to 0, and then I solved it. So x would be greater than or equal to 4, boom. All right, let's keep it moving. All right, let's do these as examples together, and then you're gonna do the beneath on your own. So denominator alert. So that means my domain restriction here is gonna come from the denominator. So I'm gonna set my denominator not equal to 0. All right. All the numbers in the whole wide world are gonna be allowed except for where the denominator goes 0. How do I solve this? Factor. This is a common factor. So I'm gonna factor out an x, And then I use the zero product property to set each factor not equal to 0. So this domain is going to be all the numbers in the whole wide world, except x cannot equal 0, or we would add 4 to both sides, or 4. All right, let's do this next one. So this next one, alert, I have 2 things that cause domain restrictions. Thing number 1, square root. Thing number 2, denominator. All right, so I know that what's underneath my square root, my argument, so x minus 4, normally for square roots, I'd say that has to be bigger than, but it could be equal to 0, because I can take square roots of 0. But I know what's in the denominator can't equal 0, right? So I'm going to get rid of this or equals to here. Okay? So what's underneath the square root has to be strictly greater than 0. It cannot be equal because of the denominator. All right? So x has to be strictly greater than 4. I've been using 4s a lot. It's kind of could have mixed it up a little bit. Oh well. It is my favorite number. Okay, so please, can you write the domain for each of these following examples? This one you're gonna have to factor a little bit. Okay, but we'll get there. Do the first one for starters. Okay, the domain for this one is all real numbers. X cannot equal 1. You'd set the denominator not equal to 0. That's how you do it. All right, try this next one, please. Okay, this one's all real numbers except x cannot equal -5. Same method, set the denominator not equal to 0, solve. All right, let's do this next one. I'm gonna set the denominator, okay, what is the answer? Let's do answers first. The answer is all real numbers except x cannot equal 2 or -2. Okay, both of those would make the denominator equal to 0. There's 2 different ways. So if I take x squared minus 4 and set it not equal to 0, if you have the difference of 2 squares as an equation, then there's 2 ways to solve it. You could factor or just solve it by like adding 4 to both sides using inverse operations. So x squared does not equal 4. Now, when you square root both sides, this is method 1 of solving, is I just isolate x using inverse operations. When I square root both sides, I must always add a plus or minus. X cannot equal plus or minus the square root of 4, okay? Because it's actually the fundamental theorem of algebra, no big deal, all right, kind of a big theorem, is that the fundamental theorem of algebra says that for polynomials, so like x squared is a polynomial, that the degree, which is 2 in this case, tells you how many answers there are. So if you have a squared, you have 2 answers, okay? Sometimes it could be like a double root, it could be the same one twice, but squares have 2 answers, always, always. Okay, so that's plus or minus 2 would be the answer, yeah? Okay, different method if you factored it. Okay, you would factor it like this and set each factor not equal to 0 and solve, and you would get this domain. Okay, all right, please go ahead and do the last one. Okay, it'd be x is strictly greater than -3.5. All right. Yeah, so I set my denominator strictly greater than 0 because it can't be equal to 0 because it's in the denominator, all right? So I take what's underneath the square root, the argument, and I say the argument of a square root has to be positive, but it also can't be 0 just because I'm in the denominator, okay? Alrighty, and that's me signing off. See you soon. Thank you, bye.